Good morning. Happy Friday. Beautiful day to do some probability questions. Uh-oh. What? Before, I guess I should have, no, we can use this to review here. I'm just going to add a page. Okay. I'm just going to snag this. I did give you a question to finish off the first chapter. We were introduced probability concepts, notation, all these facts that we need to keep track of, right? And so we'll use this example as some review. Okay. We'll do it kind of nice and slow here. If we're told that roughly 20% of undergraduates at a university are vegetarian or vegan, what's the probability that among a random sample of 3 undergraduates, at least one is vegetarian or vegan? And so first thing I'm going to do to make my life a little bit easier is to group these and call capital B. It's just going to denote vegetarian. I was going to say veg, but then vegan doesn't work either. Vegetarian or vegan. What are we told? We're given the probability of V, right? The probability of someone being vegetarian or vegan is 20%. Now, probabilities, what's the first rule of probabilities? Probabilities have to be between 0 and 1. So you want to convert them to the proportion. So the probability of A, any generic A, so any event, any probability has to be between 0 and 1. Right? And that's on your formula sheet. Okay. So we want to find, so we have a random sample of 3 undergraduates. Okay? And what we want to find is what's the probability that at least one is vegetarian. Okay? And so the next thing we want to do is figure out our sample space, right? S is going to be the set of possible outcomes, right? So I've randomly sampled 3 people, and what are my possible outcomes? Don't forget about 0, right? 0 of them could be vegetarian or vegan. Another option would be 1 of the 3, right? 2 of the 3 or 3 of the 3. We don't know which one, right? But we know it has to be one of those 4 outcomes, which means from our formula sheet, that is going to translate to the probability of something in the sample space has to be 1. One of these things has to happen. Right? So the probability of the sample space, which is a list of all the possible outcomes, right, has to be 1. Okay. What if we wanted to figure out the probability of someone being not vegan, right? And so what is the probability that someone is not vegan or vegetarian, I guess, vegetarian or vegan? That's the complement, right? So how we denote that is the probability of V with a superscript C denotes the complement of an event. Okay. And generically, the complement of an event is 1 minus the probability of V, right? Which If I told you this, and then I asked you, hey, what's the probability that someone's not vegan or vegetarian? You would say 80%, right? Because your brain already does it, right? If the probability of being vegan or vegetarian is 20%, then the remainder must be the opposite, right? And so here, 1 minus, I'll do it properly, the probability of B, which is 0.80. On your formula sheet, that's denoted by the probability of the complement of A is 1 minus the probability of A. Right? Complements just everything in the sample space that's not A generically. That was a little side gig for our review. Okay? But let's figure out this probability. Okay? We've got kind of two main ways that we could find this probability, right? And so at least one is 1 or 2 or 3, right? In my sample space, all these 3 satisfy the at least one condition. Okay. And so the probability of at least 1 is the same thing as the probability of 1. And whenever we're saying or, we're adding those probabilities. And whenever we're saying and, we're going to multiply those probabilities. Okay, so whenever you catch yourself, you want to pay attention to kind of how you say things, right? It can be 1 or 2 or 3, right? So probability of 1 being vegan or vegetarian, or 2 or 3. What could you do instead? That's a lot of probabilities to find, right? And I'll break down how to find these. But what if you leverage the complement? Or instead, right, we found the probability of this one or this one or this one. What if I just took the probability of the sample space, which we know is 1, and just lobbed off the one that we didn't want, right? That's going to be a lot easier. Okay. So, or you could say this is the same as 1 minus the probability that none are, right? Leveraging that complement. Okay, good. So now we need to find the probability that 0 of these 3 people are vegan or vegetarian. Now, how I do these is I showed you these kind of slots, right? Representing person 1, person 2, person 3. And order doesn't matter in this case. And so here I've got person number 1, 2, 3. And up above, I add the probability of whatever I want to happen, right? For person 1, if I need 0 of these to be vegan or vegetarian, right, then person 1 has to be not vegan or vegetarian, which we know the probability of is 0.8, right? And I need the next one, 0.8. And I need the third one to not be vegan or vegetarian, right? That's the only way that I could get 0 vegans and vegetarians, right? And we said, and in between these, what color can I use? And whereas here, when we were adding, we were saying or. I guess instead of this or, just so I don't bung it up more, how about I say alternatively? Too long. Right. Otherwise, the or might be confusing. So now, To find this probability, right, I just multiply through 0.8 times 0.8 times 0.8, right? I need all of these to be not vegan and vegetarian. And so this is going to be the same as 0.80 to the power of 3. Dun, 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 dun. Whoops. I get 0.512. That's the probability that none of them are, right? So that's what we want to take away from the sample space, right? So that's what I can plug in here and find, because really what I'm looking for is the probability of at least one. Okay. Or maybe I should just rewrite it down here. The probability of at least one, oops, is 1 minus the probability that none of them are, which is 1 minus 0.512. Now you could do the same thing with the probability of 1 and the probability of 2 and the probability of 3, and then add those all up. That would work, okay? It's just more tedious and time consuming, right? How would you do the find the probability of 1? Just for some practice. Oh, hey, 512. I guess I should finish this off. Got carried away. 1 minus 0.512. I get 0.488. The probability of 1, we said order doesn't matter, right? So I'm just going to make the first one be vegan or vegetarian, and the next two not, right? It doesn't matter where I put this 0.2, right? 0.2 times 0.8 times 0.8 is the same as 0.8 times 0.2 times 0.8, right? You can just rearrange them. Okay? And so order doesn't matter. And so then you would find 0.2 times 0.8 times 0.8 is 0.128. Maybe I'll do this. Should we just do it for fun? Let's do, we can do it just for some warm up, right? Probability of 2. I need a vegan and a non-vegan. Doesn't matter which order. So I'm just going to do them first, tackle what I need, and then 0.2, 0.2, and 0.8. Oops, I hit something weird. Probability of 2 in my sample of 3 is 0.032. That's small. Does that make sense? Kind of. The probability of someone being vegan or vegetarian is quite low, 0.2, right? And so then having 2 in a sample of 3, that probability should be quite small, right? Just kind of intuitively. How about, clean that up, the probability of 3. Now, a vegan. Do you expect this probability to be very, very small? I do. 0.2 to the power of 3 is 0.008. Let's see, 1, 2, 3. If you try it on your calculator, just to make sure that if it gives you scientific notation, that you know what that looks like. Sometimes there's a little E or just a space, a subtle space. And so you want to make sure that you know what that looks like. So mine gives it in scientific notation. And so you need to be able to convert it back. So now the probability of at least 1 is the probability of 1 plus the probability of 2 plus the probability of 3. which is 0.128 plus 0.032 plus 0.008. 0.128 plus 0.032 plus 0.008. Did I do it wrong? Something happened. Huh. Why isn't it working? When you guys do it, what do you get? 2 plus 0.008. You get 0.168. That's bad. Where did I go wrong? I did something wrong somewhere. Should be 0.488. I suspect. I ignored the order, but maybe order matters. And then it's more complicated. Anyways, this is the right answer. What a way to start a Friday. How's that for a review? This way's easier anyways than this mess. I don't know. I'll have to look into it. I think ignoring the order might be bad in this case. Anyways. Okay. On your formula sheet, and I have spares. If you don't have your copy, there's nicer ones and uglier ones here. But if you want one, you can have it. Like, what a flop. Oh. I'll fix it before I post the notes. How about that? You want to really get to know your formula sheet, right? A lot of these facts that we stated are given on your formula sheet. And so the general rules for probability models, right? We said, okay, probabilities have to be between 0 and 1, right? The probability of the total sample space, right? If the sample space lists all the possible outcomes, then if you roll a die, for example, one of those outcomes has to happen, right? So the probability of the sample space is 1. And then the probability of the complement of an event is 1 minus the probability of that event. Well, last day we introduced the addition rule for events A or B. Okay. Now, we did use this, in our kind of review question, right? But if you draw 3 people, for example, right, then could you have 2 of them and 3 of them be vegan or vegetarian? No, right? Has to be one or the other. And so for disjoint events, we've got this special case. So for disjoint events, sometimes we call them mutually exclusive. So you want to be aware of that symmetry. So for disjoint events, the probability of A and B is 0, right? If they can never happen at the same time, then that probability is 0. Then when you're finding the probability of A or B, you just take the probability of A plus the probability of B, and you're allowed to keep going, right? You just need to subtract the overlap if there can be any. But just in general, we only do 2. this and this is what we're going to do today. We did introduce this last day. So the special case, if A and B are independent, then, right, if they're independent, then the probability of A and B, you're allowed to just multiply them together. I usually use this in reverse, kind of flip it against itself. Okay. So we can use this fact to determine if A and B are independent. Right? To determine if A and B are independent. You don't want to assume that these probabilities are independent or these events are independent of each other. As a recap, what does it mean to be independent? It means that the probability of A is not impacted by B happening or not, right? It doesn't care about B. Whereas today we're going to focus on kind of the more common case where, okay, the probability of A happening might depend on B happening already or having happened. Okay. So that's what we'll do today. But so we can use this fact to determine if A and B are independent by checking if the probability of A and B, is it equal to the probability of A times the probability of B? So if you have these three probabilities, right, then you can multiply the probability of A times the probability of B. And if it's the same as the probability of A and B, then you can say they're independent. But they have to be exactly the same. So must be exactly the same. Ooh, how quickly can I find an example that I have? I'm going to give it a go. No. Okay. Next week I'll bring it. We can try one. So we just need to tackle the pink boxes today. Seems reasonable. We did a lot last day. We introduced all these rules, and let's see here. These guys can all be summarized by this last formula. Okay. And so here, we don't even really need this. Right? The only formula we need is the probability of A given B. We saw that last day, right? This vertical bar, you read it as given. So knowing that B happened, then what's the probability of A? Now, how you're going to find that is the probability of A and B together, right? Notice that that's just the first thing and the second thing happening. Yeah. And then you want to divide by the probability of B, which is the given thing, right? You know it happened. You can treat this, these are just placeholders for numbers, right? Probabilities are numbers between 0 and 1. And so what could you do? You could rearrange this and you could multiply the probability of B over to the left-hand side, right? So then we could rewrite this as the probability of A given B times the probability of B is the probability of A and B. Well, what do you know? Isn't that just this? Right? And so you don't really need it. The probability of A and B, I shouldn't do that. Let's put them kind of side by side. The probability of A and B, the probability of A and B is equal to the probability of A given B times the probability of B. Right. What about the next one? Oops. Oh, is the probability of A and B going to be the same as the probability of B and A? Doesn't matter, right? And so here, but what happens is the probability of A and B can be the probability of B given A times the probability of A, which really means that, sorry, I should have written this probability of B and A. B and A is the probability of B given A times the probability of A. So the only one you really need, just because A and B are generic placeholders, so the order here doesn't really matter, right? We don't even need this last one, because you can just call whatever you want to be first A and whatever you want to be second B. Okay, so these conditional probabilities, right? Now we have non-independent events, right? So conditional probabilities, this is called a conditional probability, right? It's conditional on B or given some information about B. Conditional probabilities are for non-independent. For some reason, we don't really tend to call them dependent events, but you can. There's nothing wrong with it, but dependent events. If A and B are independent, right, the special case, if A and B are independent, then the probability of A and B is still the probability of A given B times the probability of B, right? Just looking at this first one here. But if A doesn't care about B, right, the probability stays the same, then what's this going to be? This is just going to be the probability of A, right? Knowing that B happened isn't going to change the probability that A happened, right? Because they're independent. That's the definition of independence. And so then, if they're independent, then you get this special case of the probability of A times the probability of B, which is the one on your formula sheet. Which is why it shows up in that weird order, because it's actually a special case of the conditional probabilities. All right. Section 3.2, conditional probability. All right, let's get into it. I should have deleted some slides. There's kind of a lot of duplication here, so we'll see. But in this example, I have a contingency table, right, of data from 2 categorical variables, right? And so researchers randomly assigned 72 chronic users of cocaine into 3 groups, kind of avant-garde. Desipramine, which is an antidepressant. I always have to run at it. I don't know how to say it. Lithium, which is the standard treatment for cocaine, and placebo, right? Placebo being just a sugar pill usually or something like that. And the results of the study are summarized below. And so we have a total sample size of 72. So N is 72. Yeah. Looking at this table, how many of those 72 relapsed? And I don't care about what their treatment was. I only care about whether they relapsed or not, right? So then 48 out of those 72 relapsed. And so we can call that the probability of someone relapsing, right? If we have a random assignment of treatments and we randomly selected our users, our cocaine users, I guess, then right, the probability of relapse is going to be 48 out of 72. There's a question on the, hey, I already did that one. Well, let's do it properly. What's the probability that a patient relapsed? The probability, let's call this, I'll use dark blue for, let this R be relapsed. Yeah. Then the probability of R is 48 out of 72. Since there are only 2 outcomes, right? They either relapsed or they didn't, right? What's the probability? Or let's find this as a decimal because it's easier. 48 over 72. It's 2 over 3. Let's say, I'm going to use a rounded value, so I'll use approximately equal to 0.667. It's technically 0.66 repeating, but for simplicity, we'll round to 3 decimal places. What if I asked you what's the probability that they didn't relapse? You've got the table, but if all you had was this, you would say 1 minus 0.667. Right? And so, or 24 out of 72. We have an even distribution of the treatment groups, which is pretty typical, right? Because we want to have kind of an even number of participants in each group to start with. Okay? And so we've taken the 72 and we've split them evenly across the 3 groups, right? So those probabilities aren't really that interesting, right, in this case. Okay. What's the probability that a patient received the antidepressant as a, and relapsed? And you're allowed to just use the table. You don't have to use formulas if you don't want to, but these guys, right? So they had to be on the antidepressant and they relapsed, right? Which is going to be this 10 out of 72. So from the table, the probability of being on, let's call this D and this L and this P. On desipramine and relapsed is going to be 10/72 from the table. Let's try doing it with the formulas. From the table, right? We can see that that's the probability. What if we're using formulas? I jumped the gun. No, we can do it. Still have to read the table. We'll have done the next question, basically, but that's okay. From your formulas, if you have the probability of D and R, then that's going to be the probability of D given R divided by the probability of, or sorry, times the probability of R. I need more room. We know the probability of R, we just found it was 0.667. We don't know the probability of D given R, so this is the probability of being on the desipramine given that they relapse. So knowing that they're in this relapse group, right, that changes the total that we're looking at, right? And the probability of being in the first group, knowing that they relapsed, is going to be 10/48. And the probability of relapse, I'll use the 48/72. If I use the fraction, it'll cancel. If I use the rounded value, it won't cancel as nicely. And so that's why I went back to the fraction 48/72. Because now if I'm multiplying these fractions, then what happens is 48/48 goes to 1, and I'm left with 10/72, which is exactly what you had just by reading the table. Right? So you can get there either way. I'm fine with however you want to find these probabilities. Right? Doesn't matter to me. But it's nice to know that you can always get there with the formulas, right? Because they're on your formula sheet. Otherwise, you might be floundering. Okay. Any questions so far? If we know that a patient received the antidepressant, what's the probability that they relapse? We already did it, like I said. So let's bump this up here. And I did have to move it from a slide lower down, so that's why I put this little star here. So we want the probability that they relapsed given that they were on the antidepressant. That's probably the hardest part of the question, is reading that question and rewriting it in terms of a conditional probability. And so now, what do you do? If you have this conditional probability, the probability of relapse given desipramine, okay, then you can map that back to probability of A given B is the probability of A and B divided by, I guess, give me just one little line here, the probability of B. So wherever you see an R or an A, you're going to write R, and wherever you see a B, you're going to write D. Right? Which is going to be the same as the probability of R and D divided by the probability of D. From the table, we know the probability of relapse and desipramine is 10 overall out of the 72. And so this becomes, I'm just going to write it across here, keep it on the same slide. 10 over 72 divided by the probability of D. Now that's the probability of being in the desipramine group, which is 24 out of 72. Fraction over a fraction. Do you remember how to work with fractions? We don't do a ton of work with fractions, but in this chapter, we do work with fractions quite a bit. And so a fraction over a fraction, you're going to flip the denominator and multiply. So this is going to be the same as 10 over 72 times, so flip this guy, 72 over 24 and multiply. Now you have 72 over 72, which is going to go to 1, and all you're left with is 10 over 24. Which is also on the next slide, typed up. But I think it's better to just kind of get there on our own. 10 over 24 is roughly 0.4166 repeating. I'll just do 0.416 repeating. Or approximately 42%. You want to be round and round like crazy, which they do in these slides. Nice. So the conditional probability, right, usually involves a fraction, right? The probability of A and B over the probability of B. But we have the table, and as long as you kind of talk yourself through it, go nice and slow, you'll be able to pull those probabilities. I feel like we just did this, didn't we? What's the probability? Oh yeah, this is the one that I wanna done earlier. If we know the patient, what's the probability? Okay, this one's different. If we know that a patient relapsed, what's the probability that they received the antidepressant? That's a different question. If I'm not reading it wrong. First thing you want to do is figure out, okay, how do you translate this into probability notation? Because that's going to be the easiest way to work with this. Or if you're able to read it from the table, that's cool. If we know the patient relapsed, so we know they're here, what's the probability that they received the antidepressant? the 10 over 48. The probability of D given that they relapsed is the probability of D and R over the probability of R. Which is the probability of D and R is 10 over 72. And the probability of relapse is 48 over 72. And once you flip and multiply those, it's very similar to what we just saw. 10 over 72 times 48 over 72, but you flip it 72 over 48. And then that's how you cancel these 72s, and you're left with 10 over 48. 10 over 48 is roughly 0.20833, which is different from the one that we just did. Right. Same idea though, but we just did the probability of relapse given the desipramine versus the probability that they were on desipramine given that they relapsed. Right. Kind of different situations. If we know that a patient relapsed, what's the probability that they received the antidepressant? So now we can find the probability of desipramine given relapse. That's the one we just did, right? 10 over 48, right? So now we're just focusing in this column here, and we can find the probability that they were on lithium and they or given that they relapsed, which has a higher probability, right? And the probability that they were on the placebo knowing that they relapsed, right, is even higher. From these numbers, these guys here, do you suspect there's a treatment effect? I suspect there might be, right? Knowing that probabilities are only between 0 and 1, right? So then 0.21 and 0.42, for example, they're quite far from each other, right? And so if there was no treatment effect, what would you expect? You would expect all of these to be roughly the same, right? And so here, since these probabilities are quite different, we suspect there is a treatment effect. We suspect there is a treatment effect. Right? Knowing that they relapsed tells us something about the treatment. Or that there's a relationship between relapse and the treatment. So for now, all we have is this gut feeling, and later in the course, we're going to develop kind of techniques to figure out if there is a significant difference in the treatment groups. But for now, we just trust our gut. Okay, we have already talked about this, where we talked about, okay, the special case of the independent probabilities, right? But now if we flash forward to A and B, any two outcomes, then the probability of A and B is the probability of A given B times the probability of B, which is on your formula sheet. Okay? And as it says here, this is just that conditional probability formula. rearranged, which we already saw. Consider the following hypothetical distribution of gender and major of students in an introductory statistics class. So now we have a gender variable, which is a categorical variable, and we have whether they were a social science major or not, right? Just lump everyone into not social sciences, which is kind of we understand that there are other majors, right? But maybe if the one that we're most interested in is the social science majors, then we can just lump everyone into the not social science category, boiling it down to only two outcomes. The probability that a randomly selected student is a social science major is this 60 over 100. Now, the probability that a randomly selected student is a social science major, given that they're female. So now knowing that we're here in this female group, now my totals out of 50 instead of 100 is 30 over 50, which is still 0.6. So because the probability of being a social science major, given knowing that they're male, right, is also 0.6, then we say that the major of the students in this class does not depend on their gender. Right? So from here, if we kind of wrote this down, this is the probability of being a social science major. Social science, for simplicity, let's change this to F. And then this is the probability of being a social science major given F, just so that they match. It is true for the males as well, right? They had the same distribution, 30-20, 30-20 out of 50, right? And so it is true for the males as well, but let's just match up what we have. And so then what we say is, because the probability of the social science, knowing that they're female, is the same as the probability of being social sciences, that means that they're independent. We've already worked through this, but it doesn't hurt to talk about it because it's kind of an obscure thing. So if we have the probability of A given B, then if that is the same as the probability of A, then we say that these two things are independent. Which makes sense, right? Knowing something about B, well, it doesn't impact the probability of A just by the definition. So then we could say that the probability of A given B, we can rewrite it just like we were doing the probability of A and B over the probability of B, right? But if they're independent, then the probability of A and B is just going to be the probability of A times the probability of B, which, if they're multiplying up top, then the probability of B over the probability of B goes away and goes to 1, and all you're left with is the probability of A. But if you kind of got that from the beginning of class, you did it. Right? It's just kind of solidifying things. And I think I got ahead of myself. So what are these problems going to look like? This is kind of an advanced version of these problems, but kind of interesting. Now, before we start with this example, hey, I want to introduce something called tree diagrams. And so to solve any probability problems, but definitely conditional probability problems, we often use a tree diagram. A tree diagram is going to be useful if you're able to break it down into a first event followed by a second event. So especially useful if we can reformulate the question into a first event followed by a second event. Now, what that's going to look like is, let's just focus on each event. Right? The first event has only two possible outcomes, and the second event only has two possible outcomes. We can extend this, but let's just focus on each event only has two possible outcomes. And we've seen how to make that happen, right? Either you're a social science major or you're not, right? There are others, but you can lump them into a not category, right? Take the complement. Now, what this is going to look like, and how I usually do my tree diagrams, is you want to make sure you give yourself lots of room. Here are the first two possible outcomes for the first event. So the first set of branches denote the first event. Then it doesn't matter what happened in the first event. So for example, let's say the first event is, did you get an A on test 1 or on the midterm, let's call it A on the midterm. Let's call that M. For midterm. Because then I want to talk about, did you get an A on the final, right? And so then I'll use F for the final, because they're both talking about A's. And so if I use A right away, then it gets kind of boggy. But let's say you write your midterm and you got an A, or what's the alternative? You didn't get an A. Right? That's the first event. The second event is the next set of branches. Let's say, for example, getting an A on the final. Let's call that F. Which is kind of ironic, I guess. So now, if you got an A on the midterm, right, then there are two possible outcomes still, right? You could get an A on the final. That's great. Or not. you're not hooped if you didn't get an A on the midterm, right? You're still able to get an A on the final. And you're still able to not get an A on the final. Do you think getting an A on the final, so there are two ways of getting an A on the final, right? Here or here, right? Do you think the probability of getting an A on the final is going to be higher or lower knowing that you got an A on the midterm? Probably higher, right? Higher than getting an A on the final if you didn't get an A on the midterm, right? And so now we have these conditional probabilities, right? Knowing the outcome of the first event determines the probability of the next outcome. Yeah? And so here, right, these we would consider kind of conditional probabilities. So usually I just write the F and the not F and the F and the not F, but really what I mean and what I should be writing is technically the probability, or F, knowing they got an A on the midterm. Right? And this is not getting an A on the final, knowing they got an A on the midterm. Right? And this is getting an A on the final, given they didn't get an A on the midterm. And this is technically not getting an A on the final, given they didn't get an A on the midterm. Those are the events, but really we're trying to find probabilities, right? And so on each of these branches, we can attach probabilities. I'm just going to make some probabilities up. Let's say the probability that you got an A on the midterm is what? 0.8. Wow. That's great. Then you also know the probability of not getting an A on the midterm is what? 0.2, right? Because in the first event, there's only two possible outcomes, and so you can use the complement. In fact, all these branches in the same level have to add to 1. Yeah. I'll call it a set of branches must add to 1. So you can have more than 2 outcomes, but for simplicity, we're just considering 2 for each. So for my probabilities then, right, how about I just sneak some probability notation around these conditionals, right? Because it'll save me a little bit of writing, but also that's what we're after, right? Let's make up a probability of getting an A on the final, knowing that you got an A on the midterm. Let's make that 0.9. Pretty good. Which means the probability that you don't get an A on the final, knowing that you got an A on the midterm, has to be 0.1, right? The set of branches has to add to 1. Oops, sorry, 0.1. And let's just make up another probability here. If the probability of getting an A on the final, knowing that you didn't get an A on the midterm, let's make that 0.6. Why not? Doesn't matter. Then the probability that you don't get an A on the final, knowing that you didn't get an A on the midterm, is 0.4. So the probabilities of getting an A on the final, right, 0.9 versus 0.6 depends on what happened on the midterm, right? Conditional on what happened on the midterm. And I need this space, so can I bump it up here instead? Sneaky. If I want to find what's the probability of getting an A on the midterm and on the final, how are you going to use this tree diagram? A midterm, so you have to get an A on the midterm and an A on the final. When you're saying and, you're going to multiply these probabilities. And because these are the conditional probabilities already, right, then that's safe, right? And it's especially easy if they're just independent events followed by each other, right? Then you just multiply down the branches, and that's going to be M and F. So here, at the end of this branch, for each branch, this is going to be the probability of M and F. Now, from the formulas, we know that that's the probability of M times the probability of F given M. But that's just really multiplying down the branches. So that's all you really need to know. The probability at the end of each branch is just multiplying down the branches. And that's why it's easier to use a tree diagram. Or the probability at the end of each branch. Branch is just multiplying down the branch. That's easier to remember than remembering all this notation. Yeah? And so I'll give you this proper version, but then for the example, I'm going to show you how little you actually have to write out. Okay. And so this is all the proper notation and what we kind of should be writing and what we're doing. But in the end, you'll be pleased to find it's not very much. Yeah. So this is going to be 0.80 times 0.90, which is 0.8 times 0.9 is 0.72. So down here, I get the probability of ending up at the bottom of this branch is 0.72. You do the same thing, 0.8 times 0.1. Then you get 0.08. You do the same thing here, 0.2 times 0.6. I get 0.12. And then finally, 0.2 times 0.4, I get 0.08. This is a set of branches, right? And so how I can check my work is as long as I haven't done any rounding, right? If you've done some rounding, then you need to be a little bit more lenient, but these should all add to 1. So 0.8 plus 0.08 plus times 0.12 plus 0.72. Phew, it does add to 1. So that's one way to check that your math is working, right? All of these have to add to one. This is a set of branches. Okay. What if I want to find the probability of getting an A on the final? There are two ways that can happen, right? If you look down your branches, okay, scenario one, great, you got an A on the midterm and you got an A on the final. Okay. Or the other option is you didn't get an A on the midterm, but you got an A on the final, right? So then the probability of getting an A on the final overall has to be 0.72 or 0.12, right? Because you're saying or between these branches. It can't both happen at the same time. So then you're going to add those probabilities. This is the same. The probability of an A on the final is the probability of an A on the final given an A on the midterm plus the probability of an A on the final given not an A on the midterm. Right here, you're going to catch yourself saying or. Oh gosh, don't look. What did I do wrong? Not my day today, I guess. Which is kind of weird, but I should be saying and. Which is at the end of each of those branches, which was 0.72 plus 0.12. 0.72 plus 0.12 overall probability of getting an A on the final is 0.84. Ah. What if you had to find the probability of getting at least one A? That can be on the midterm, or it can be on the final, or it can be both, right? So now if we have this, and you already have all these probabilities listed, then what you want to do is you want to figure out all the branches that satisfy your criteria, right? At least one A. If you got an A on the final or on the midterm, you did it. You got at least one A. And then if you got an A on the final, that's cool. Then you have two A's, but that's still at least one. So this one would satisfy that. An A on the midterm, well, I already got at least one. So I'm still good. That one satisfies it. Or if I didn't get an A on the midterm, if I need at least one A, then I would have to get an A on the final to satisfy that criteria. The only one that doesn't satisfy it is that far right branch, right? So whether you wanted to add up these probabilities, now that you have them written out, that's kind of easy, right? But you could also do what? You could use the fact that they all add up to 1 and just subtract the one you don't want, just like we were doing, right? So whenever you're seeing at least something, you want to try to think about, okay, maybe it's going to be easier if I just take the complement. Right? I'm going to remove these check marks because they might not make sense to someone looking, because I didn't write that one down, right? But those are all the things that we'll be able to do with a tree diagram. Okay. Any questions before we do this example? Okay. The American Breast Cancer Society estimates that about 1.7% of women have breast cancer. Susan G. Komen for the Cure Foundation states that, and I never know how to say this, mammography correctly identifies about 78% of women who truly have breast cancer. And an article published in 2003 suggests that up to 10% of all mammograms result in false positives, right? What's a false positive? If you don't have cancer, which we're told here, for patients who do not have cancer, this is testing positive when we shouldn't. Obviously, these does have a note here, but these percentages are approximate and kind of outdated, probably from 2003, but just generally difficult. But we're going to use these percentages to answer some questions. Now, the first thing I want you to do, or we're going to do together, and on the test and on the final exam, so it's worth kind of exploring. I'll give you a situation not as difficult as this, but kind of like this. And first thing I'll get you to do is draw the tree diagram with all the appropriate probabilities. And so I want to show you what I mean by that. In the slides, they go through and kind of answer it, but we're just going to do it together instead. So here, as an example, draw the tree diagram with all the appropriate probabilities. As promised, I'm going to try my darndest to only write the stuff that I need to see for full marks. Okay. One of the hard parts here is going to be figuring out, because if I'm asking for a tree diagram, then you know that you need to break it down into kind of a first event, second event scenario, right? There will be clues, right? If you're given conditional probabilities, then that has to be in the second event, right? Looking at this example that we did here, right? All these conditional probabilities have to be in the second event, right? Conditional on the first event happening. So that's going to be a clue. In this case, what are the conditional probabilities that we've been given? So overall, 1.7% of women are estimated to have breast cancer. Relatively low, right? But 78% of the women who truly have breast cancer. So this is a conditional probability, right? And so here, this is our conditional probability, right? Given that they have breast cancer, then what's the probability that they test positive? And so that's going to tell me that, okay, then the first set of branches is, well, does this randomly selected woman have cancer or no, right? And so we have that probability, that overall probability, or we're given that. Yeah. So that's kind of a first hard thing to tackle. Let's see here. For some shorthand, I'm going to let C represent cancer, which means not C, or the complement of C is not cancer. Often I'll read it as not C, just to emphasize that it's the complement. I'm going to say, just use a plus for positive. You can use P or something, but this is going to be a positive test. And then you can use a negative or a positive C, which in this scenario I find kind of counterintuitive. And so you can use a negative or the complement of a positive to denote a negative test result. This is going to be how we set up our tree diagram. So our first set of branches, you want to give yourself lots of space, putting in the center, right? And we have, first, they could have cancer or not. And all I really need to see, I don't need to see the notation or anything. All I really need to see are the probabilities below here. I do need to see which branch is which. Otherwise, it's going to be really hard to follow your work, right? And so you do need to identify which one is which and what the probabilities are underneath each branch. So 1.07% is very, very small, right? And so that's going to be 0.017. 1.7 divided by 100. Had to check. But also, I need it here. How do I find the probability of not cancer? You can probably just kind of get there, right? 1 minus 0.017. I guess this is a specific cancer, but still. 0.983. So there's a very high probability that a randomly selected woman does not have breast cancer. Right. Okay. So that's all I really need to see in that first set of branches. What's the follow-up event? Now we do a test, right? We do a mammogram, and it either gives a positive result or a negative result. Or you could use the complement if you want. And if you don't have cancer, you could still get a positive result, and you can still get a negative result, right? These probabilities are going to be different depending on which initial branch you went down, right? And so let's grab those probabilities. So correctly identifies, let's think about that, what that means. About 78% of women who truly have breast cancer. So knowing that they went down the cancer branch, then the probability of being correctly identified is 0.78. Correctly identified in this case, right, knowing that they have cancer, should be a positive test, right? And so the probability of going down that positive branch, given that you're going down the cancer branch initially, is 0.78. So here I write 0.78, which makes the probability of testing negative 1 minus 0.78, which is 0.22. Okay. 10% of all mammograms result in false positives for patients who do not have cancer. So knowing that they went down the not cancer branch, right, then the probability of a false positive, which is a positive when you shouldn't, right, is 10%. Okay? And so now you don't have cancer, but the probability of testing positive is 0.1. Which means then the probability of testing negative is 0.9. At the end of each branch, I have the combinations. And so usually I'm kind of sloppy and I just write C plus, which really is shorthand for C and plus or positive, right? Cancer and testing positive. But it's really just so I can keep track of what the outcome at the end of each branch is. Right? C minus, C complement plus, and C complement minus. Remember, I'm just showing the work that you need to show. The last thing that I want when I say with all the appropriate probabilities is the probability at the end of each branch. Right? I want you to do that just so that you can check that they all add up to 1, right? That's a good way to make sure that you set up your tree so that it's working, right? And so here, if I go down each branch, 0.017 times 0.78, I get, and try not to round, right? If it's giving you kind of just, in this case, I get 5 decimal places. I think that's pretty reasonable to write down. So I'm going to do 0.01326. 0.017 times 0.22 is 0.00374. 1, 2, 3. 0.983 times 0.1 is 0.0983. And 0.983 times 0.9 is 0.8847. Right? Because I didn't round anything, these should add to 1. So if I add these all up, plus 0.0983 plus 0.00374 plus 0.01326, whew. I just do a little side note. That's more for me. I guess you don't have to do that for full marks. How do I change the style? Make it optional. That's more for you for checking your work. Okay. So now I'm feeling good about all these probabilities. Now we can answer some questions. Let's grab this one. I usually put quite a few marks on the tree diagram, right? Being able to set this up and then using it to answer some questions, right? Using your tree diagram, that's fine. But setting this up is a lot of work, right? So usually that's a lot of marks. And by a lot, I mean like 4 out of 7. Something like that. Nothing's worth a lot of marks, but still. You can make it 40 out of 70 if you want. I always find it's really funny when people ask me, well, what's the test out of? I don't know, it doesn't matter. It's out of 30,000. Just inflate all the totals. It's not. It won't be, because that's hard. Okay, when a patient goes through breast cancer screening, there are two competing claims. Either the patient has cancer or the patient doesn't have cancer, right, as we established. If a mammogram yields a positive result, what's the probability that the patient actually has cancer? Okay. And so here, you want to rephrase this in terms of a conditional probability. And so knowing that you get a positive result, what's the probability that they actually have cancer? And so we want to find the probability that they have cancer given a positive result. You take this and you just kind of roll it out like we have been doing. Then using the formula on your formula sheet, right, you take the first one and the second one in the numerator, cancer and a positive result. And then you divide by the second one, the probability of just the second one on its own. Okay. This is where it usually gets a little bit sneaky, but it'll always behave the same way, right? And so if you think about the probability of cancer and testing positive, right? If you map down your branches here, you have to have cancer and you have to test positive, then you know that probability is 0.01326 because you already found it, right? And so here, this is going to be 0.01326. From above. You already did all that work. Now we just use the probabilities that you found. The probability of testing positive. We have two branches where that can happen, right? And so here I can test positive if I have cancer, but there's also some probability. In fact, the probability is 0.0983 that I test positive even if I don't have cancer, right? And so now the probability of just testing positive overall is going to be this or this, right? And so you need to take that into account. And so over the probability of cancer and plus, or probability of not cancer and plus, using my shorthand, right? Ditching the and. If I smush them together, it has to be both. Which is going to be 0.01326 divided by 0.01326. And I know that's kind of confusing using the same number again, but it's going to be rolled up with 0.0983. So they're not going to cancel or anything because I'm adding them. Yeah. And so I get 0.01326 plus 0.0983. You're more than welcome to figure out what the probability of testing positive is separately and then incorporating it, right? But I just want to show you that you could do it all in one go. So 0.01326 plus 0.0983, 0.11156. Oops, sorry, divided by. There, sorry. Just focused on the denominator. So now if I do 0.01326 divided by 0.11156, get 0.118859864. Which if we simplify it a little bit, right, and just talk in terms of percentages, right, that's roughly 12%, right, 11.8859, blah, blah, blah. Let's round it to 12% so it's easy to think about, right? And so then the probability of having cancer, knowing that you tested positive, right, is 12%, right? And so it's kind of interesting, right? Incorporating these conditional probabilities. So therefore, the probability of having cancer given a positive test is about 12%. Right, just kind of translating, zipping it up to a nice clean percentage, mostly because that's what they use later. So I like to keep all my decimal places, but 12% is easier for us to wrap our heads around, I think. Okay. Nice. Any questions about that one? This is our first one, kind of tricky. I'll say C above because we already did it. They set it up in a different way, but can convince myself that they're the same, right? And you're welcome to kind of set them up this way. Then you can write across instead. It's just ingrained in me to do it down, but it's okay. This reads nicer. And I suspect it was easier to program. How about this one? Suppose a woman who gets tested once and obtains a positive result wants to get tested again. In the second test, what should we assume the probability of this specific woman having cancer is? That's the one that we just found, right? We know the probability of having cancer given a positive result is roughly 0.12 from before, right? So now, if we were to make a new tree diagram, right, we would have to adjust the probability of having cancer. If we do a second test, right, we would adjust the probability of them having cancer. From earlier. What's the probability that this woman has cancer if a second mammogram also yields a positive result? So now, our tree diagram we have to adjust these probabilities, right? The probability that they have cancer now is 0.12, quite a bit higher than 1.7%, right? And so now it's 12%, quite high. 1 minus 0.12 is 0.88. The probabilities of testing positive and negative, knowing that they have cancer or not, they'll stay the same. I think it was 0.78. and 0.22 and 0.1 and 0.9. Right? This is the change. Right? Now that we're heading into a second test, right? The probability that they have cancer, we have to adjust that. Right? There's still an 88% chance that they don't, right? So now let's translate this question into a conditional probability statement. So what's the probability that this woman has cancer if we get a positive result? So the probability of cancer given a positive result. That's going to be the probability of cancer and a positive divided by the probability of a positive. These values are all going to change now because it's the second test, right? And we can go through and we can calculate all the probabilities, but because I'm running out of time, how about I just circle the positive results and find those probabilities, because as we saw, those are the only ones that we're going to need. So if I multiply down each branch, I get 0.12 times 0.78, which gives me a probability of 0.0936. And then the next branch that I'm interested in is 0.88 times 0.1, 0.088. So this is going to be the probability 0.0936 of cancer and positive. And then testing positive can happen in two ways. So 0.0936 plus 0.088. Makes 0.0936 divided by 0.1816. I get 0.515418,502, blah, 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 blah. Or roughly 52%. Which means the probability that she has cancer after a second test, a second positive test, in my opinion, is still only 52%. So should you do a third test? Probably, right? Just to make sure. Because then what would you do? For your third test, what would happen to the probability of the cancer would be 0.52, right? Still, these probabilities would be the same, right? But it would adjust the probabilities at the end of each of the branches, right? And so then you become increasingly confident in the diagnoses if you do multiple tests, right? Not just one. Yeah. We're not going to call it Bayes' theorem, but what we're doing is called Bayes' theorem. And so this is kind of hand wavy, and we could try it. But here's a kind of a similar question that I want you to try on your own. Try on your own. When do I see you? Not until Wednesday? Oh my gosh. Just one little application problem standing between you and the weekend. Or you can try it Tuesday night or something. Doesn't matter to me. But now it's fresh. It does have the results in the slides, so you can check. But we'll use it as review next day. Any questions? Okay. Enjoy your weekend. Sun's out. I'll see you on Wednesday.